Welcome to the lecture series of partial differentiation. In partial differentiation, in previous lectures also, applications of partial differentiation we discussed. Mainly, in last lecture, an application of partial differentiation in Jacobians. Is how to find out the Jacobian. Jacobian is what? It is nothing but the determinant of partial derivatives. And Jacobian is highly used in phase transfer. Now, we are going to discuss one of the applications of Jacobian, that is functional dependence and independence. So when there are two functions or more than two functions, we need to check whether they are dependent or not. If they are dependent, then for analysis purpose, it can be considered. So first of all, we have to check they are dependent or not. Given functions are dependent on. Function may be anything. It's velocity function, the speed function, the displacement function. So in that way, we can find out the functional dependence of two variables. Functional dependence of two variables. So what is functional dependence? In applications of partial differentiation, the functional dependence, I tell you. What is meant by functional dependence? It's when two variables are functionally dependent. So I tell you the definition of functional dependence. If u and v are functions of x and y, u and v are functions of x and y. If u and v are functions of x and y, said to be functionally dependent, if Jacobian of u and v with respect to x and y, or this can be written as del of uv by del of xy is equal to 0. This Jacobian is 0. Jacobian of u and v with respect to x and y is 0. Then we can say u and v are functionally dependent. Now the first problem on this topic, show that the following functions are functionally dependent. Following functions are functionally dependent. So that the following functions are functionally dependent. In short, I will be writing ft. Okay. So that the following functions are functionally dependent. Also find relation between them. Also find relation between them. The functions are given. U equals sin inverse x plus sin inverse y. V equals sin x under root 1 minus y square plus y under root 1 minus x square. These two functions are given. You may be given any functions. What is the question here? We have to show u and v are functionally dependent, and also we have to find out the relation between u and v. Then if you look at this function, so here we have trigonometric function. Okay, we have here inverse trigonometric function, and in v we have algebraic function. We have only x and y here, and here we have trigonometric function or inverse trigonometric, whatever. So what we have to do, we have to select the trigonometric formula so as to fit these two variables u and v. But when you find relation between u and v, so there should not be x and y, it must be free from x and y. That relation will be exclusively in terms of u and v. The first part is what? First part is to show functional dependence of these two variables. We are going to solve it. Now the Jacobian I am going to find. The Jacobian of UV with respect to xy I am going to find. Okay. And Jacobian is what? By definition of the Jacobian, it is del u by del x, first row for u and the second row for v. Second row for v. Okay, by definition of the Jacobian I have written, because Jacobian is nothing but the determinant. Now we want del u by del x, del u by del y, del v by del x and del v by del y. Okay, all those partial derivatives are required. Means these four partial derivatives are required. Now what I am going to do, I am going to find out partial derivatives separately. Okay, u is sin inverse x plus sin inverse y. So del u by del x means partial derivative of u with respect to x keeping y constant. In partial derivative we keep other variable constant. Derivative of u with respect to x keeping y constant is what? Derivative of sin inverse x with respect to x is 1 by under root 1 minus x square. And derivative of sin inverse y is 0 because we are treating y constant. When you take partial derivative with respect to x, derivative of this is 0. Plus 0 I am not writing. Then del b by del x I am writing here. Del u by del y I am writing. Del u by del y is what? Partial derivative of u with respect to y keeping x constant. This derivative of sin inverse x with respect to y is 0. I am talking about the partial derivative. And derivative of sin inverse y with respect to y is 1 by under root 1 minus y square. Okay, these two derivatives we found. Now coming to v, v is what? X under root 1 minus y square plus y under root 1 minus x square. Take partial derivative of v with respect to x keeping y constant. See, root of 1 minus y square is constant term. Derivative of x is 1. This 1 in the multiplication, no need to write. And here y is constant. We are taking derivative with respect to x, keeping y constant. Y is multiplicative constant as it is, and derivative of under root 1 minus x square. Derivative of under root 1 minus x square with respect to x is what? Derivative of 1 minus x square. Under root 1 minus x square means derivative of 1 minus x square power 1 by 2 is what? 1 by 2. 1 minus x square raised to power minus 1 by 2. Okay, means this can be written as 1 by 2 as it is under root 1 minus x square. 1 by under root 1 minus x square. Is it? So this is derivative of under root 1 minus x square with respect to x is 1 by 2 under root 1 minus x square. Is it? This is del v by del x. Now del v by del y, take derivative of v with respect to y keeping x constant. The x is multiplicative constant. Okay. And one more thing I left here. Derivative of 1 by 1 minus x square raised to power 1 by 2 is what? 1 by 2 1 minus x square raised to minus 1 by 2 means derivative of like this. Derivative of x to the power n is n x to the power n minus 1. So one more thing I left here, the derivative of this argument x again I have to write with respect to small x, and derivative of 1 minus x square is what? Minus 2x I have to write here, minus 2x. This, okay, in the multiplication this 2 gets cancelled. Okay, and derivative of this will be what? Then x by minus x by this one minus x by this 2 gets cancelled. Minus x by under root 1 minus x square is derivative of this. See, the derivative of this is what? Minus x by under root 1 minus x square. minus 2x is the derivative of the 1 minus x square in the multiplication, and this 2 and this 2 gets cancelled, minus x will remain as it is, and this I have taken in the denominator. Okay. Now derivative of, similarly, derivative of 1 minus y square raised to power 1 by 2 with respect to y will be what? It will be what? Just like this, y by under root 1 minus y square. Derivative of this minus. Okay. Now derivative of this with respect to y, keeping x constant, the derivative of y with respect to y is 1, and 1 minus x square is a constant because we are taking derivative with respect to y. So this is a very important thing. This thing is very important because you have to take derivative very carefully. If you are wrong for derivative, these entries, then functional dependence and independence, it cannot be judged in a correct way. These four derivatives are important. Okay. Now what I am going to do, I am going to write the Jacobian. This I am going to write here. We have space. I am writing short here. See, del u by del x is what? 1 by under root 1 minus x square. 1 by under root 1 minus y square. Okay. Then del b by del x is what? Del b by del x, see, under root 1 minus y square minus xy by under root 1 minus x square. Del b by del y is what? Minus xy by under root 1 minus y square plus under root 1 minus x square, like this. Okay. So values of these four derivatives, partial derivative, this derivative I put here, this derivative I put here, value of this derivative, value of this derivative. Now, so this is main flow of the solution. The required partial derivatives I found separately. Now this I am going to solve. Okay, this thing I am going to solve. See, what is it? The determinant. Once again I am writing 1 by under root 1 minus x square is the first entry. Second entry of the determinant is this thing. Is it? See here under root 1 minus y square minus xy. Next entry under root 1 minus y square minus xy. This divided by under root 1 minus x square. Is it? Now the fourth entry is this entry, minus xy by under root 1 minus y square minus xy by under root 1 minus y square plus under root 1 minus x square. Okay, the same thing I have written. Okay, I changed the sheet. That's why same thing is this I have repeated. This thing I have repeated here. Now try to solve this determinant. So how to solve 2 by 2 determinant is very simple. Product of these two elements minus product of these two elements. So I am going to multiply this 2 1 by under root 1 minus x square multiplied by minus xy by under root 1 minus y square plus under root 1 minus x square. Okay, product of these two, these diagonal elements. Now minus product of remaining two, 1 by under root 1 minus y square, this multiplied by 1 minus y square in root minus xy by under root 1 minus x square. Is it in this way? Now have the multiplication and check whether you get 0 or not. This is equal to, See, product of this is what? Minus xy by under root 1 minus x square into 1 minus y square. Product of these two is plus 1. Product of these two is minus 1. Minus minus plus here. Product of these two elements xy by under root 1 minus y square under root 1 minus x square. Okay. Now these two are same with opposite sign. This will get cancelled. 1 minus 1 is 0. So in this way I am getting 0. So what we have shown here, the Jacobian means this Jacobian. See, this Jacobian value I have calculated and it is coming to be 0. If Jacobian is 0, therefore u and v are functionally dependent. Okay, these are functionally dependent. Is it? Functionally dependent. Now, what is the second part? Second part is to find out relation between u and v. What is u? U is sin inverse x plus sin inverse y. This is u. And v is what? See v here. V is what? This is v. X under root 1 minus y square. X under root 1 minus y square plus y under root 1 minus x square. Okay. This u and v are given to you. Now we are going to find out relation, but they are functionally dependent. If dependency is there, you can find out the relation. Because whenever dependency is there, if dependency is there, then we have relation, is it? Otherwise not. So u and v are functionally dependent, that we have done. Relation between u and v is going to find. Now, as I told you earlier, in u we have trigonometric function, in v we have only algebraic function. So in this case, use a proper trigonometric formula. Because when you use trigonometric formula, so you will be getting relation between u and v. But in that relation, you must have the removal of x and y. There should not be x, there should not be y. Only that relation must be in between u and v. See, what I am going to do, you can solve by your way also. What I am going to do, this is our equation 1, this is our equation 2. So I am going to let, for the sake of simplicity only, you can directly use the formula. For the sake of simplicity, I am going to let a is equal to sin inverse x and b equals sin inverse y. Therefore, this equation 1 becomes u is equal to a plus b. Okay, u is equal to what? A plus b. U equal to a plus b. Now, b is equal to what? X. X is what here? X is sin a. Sin inverse x is a. Therefore, x is sin a. And y is what? Sin b. Okay, so I am putting those values here. X is sin a under root 1 minus y square. Y square means sin b whole square or sin square b. One and the same thing. Plus y. Y is what? Sin b under root 1 minus x square means sin square a, because x is sin a. Now sin a under root of 1 minus sin square b is what? It is cos b. It is very clear. And sin b, and this is again trigonometric formula. It is cos b. This is b we are solving. Now sin a cos b plus sin b cos a, this is a, no? This is a. sin b cos a, then we have trigonometric formula. This is the expansion of sin a plus b. Sin a plus b, sin a cos b, and cos a sin b. Therefore, v is equal to sin of a plus b. A plus b is what? U. So in this way, we found relation between u and v. In this way, we found relation between u and v. So in relation, that relation should be free from x and y. Remember, relation should not contain x and y. Now the second sum we are going to take. I'll increase a little bit speed of writing now. The same problem. Okay, same problem. Try to understand. Say here, if u is equal to x plus y by 1 minus xy and v equals tan inverse x plus tan inverse y. Is it? Then show that u and v are functionally dependent. U and v are functionally dependent. Also find relation between them. Also find relation between them. It's u and v. Okay, same problem. Only u and v are changed. Here again, u is algebraic function, v is trigonometric function. In previous sum, u was given in trigonometric form and the v was given in algebraic form. Okay. Now, without wasting time, I am going to find out the Jacobian of u v with respect to xy. Is it? By definition of Jacobian, del u by del x, del u by del y, del v by del x, and del v by del y. Okay. This is main flow of the solution. So how many derivatives are required? Here we require 4 derivatives. So all those 4 derivatives I am going to find out separately. Okay, all those 4 derivatives I am going to find separately. So u is given to you. U is sin u x plus y by 1 minus xy. Now take derivative of u with respect to x, keeping y constant. Because del u by del x is required. Take derivative of u with respect to x, keeping y constant. We are taking derivative with respect to x. X is present in numerator and denominator also. So I am using quotient rule of the derivative, u by v rule or quotient rule. The quotient rule is what? Denominator square. Okay. Numerator I am writing. Denominator. Derivative of numerator, derivative of x plus y with respect to x, keeping y constant. Derivative of x is 1 and derivative of y is 0, minus numerator and derivative of denominator with respect to x, keeping y constant. Derivative of 1 is 0 and derivative of xy with respect to x is minus y. Derivative of 1 is 0. Derivative of xy with respect to x is minus y, because derivative of x is 1 and y is multiplicative constant. So you can solve it further. 1 minus xy, if possible, you are free to solve. Minus minus plus xy and minus minus plus y square. Denominator is same. 1 minus xy square. Okay, this is equal to xy minus xy will get cancelled and 1 plus y square by like this. Denominator is same. Okay. Now del v by del x I am going to find. Del u by del y I am going to find first. Okay. I have taken derivative with respect to x, keeping y constant. Now I have to take derivative with respect to y, keeping x constant. Y is variable now, x is constant. Here y is present in denominator as well as in the numerator. Again quotient rule I have to apply. What is the quotient rule of derivative? Denominator square. Denominator. Derivative of x plus y with respect to y is 1, because derivative of x is 0, derivative of y is 1, minus numerator x plus y, and derivative of denominator 1 minus xy with respect to y, derivative of 1 is 0, and x is constant, multiplicative constant, and derivative of y is 1, means minus x is the derivative of 1 minus xy with respect to y, keeping x constant. Now again I am going to simplify it. See, 1 minus xy as it is, minus minus plus x into x square and x plus xy. This divided by 1 minus xy square, and this is coming to be xy minus xy gets cancelled, 1 plus of x square by 1 minus xy whole square. Is it? This is a del u by del y. Now I am going to find out. I am going to find del v by del x and del v by del y. These 4 derivatives you have to find very carefully. 4 derivatives very carefully you have to find. See, v equals tan inverse x plus tan inverse y. This is given. Now del v by del x is equal to derivative of tan inverse x is 1 by 1 plus x square. Derivative of tan inverse y is 0, and derivative of this with respect to y, keeping x constant, is what? Derivative of tan inverse x with respect to y is 0, and derivative of tan inverse y is 1 by 1 plus y square. In this way, these all 4 derivatives we found, because these derivatives are required. These derivatives are required. These 4 derivatives separately are found. Now putting those values here, see, I am putting here those values equal to this determinant del v by del u by del x is what? 1 plus y square by 1 minus xy whole square. Del u by del y is what? 1 plus x square 1 minus xy whole square, and del v by del x is 1 by 1 plus x square. Del v by del y is 1 by 1 plus y square. Okay. If you solve this, have a cross multiplication, product of these two, and write directly 1 minus xy whole square, product of these two, because 1 plus y square will get cancelled if you multiply these two terms, minus product of these two, 1 plus x square will get cancelled, and this will remain. Again these two are going to become cancelled, means 0 and this implies u and v are functionally dependent. They are functionally dependent. If u and v are functionally dependent, then you don't waste on finding relation between them. Now for relation, u is given. Once again I am writing this function, and v is given to you. But here in u and v containing trigonometric function and u is only algebraic function. U contains only algebraic function. So in this case we have to use the formula, and we know the formula that here directly tan inverse of xy by x plus y by 1 minus xy is equal to tan inverse x plus tan inverse y. Okay, and this is the formula, trigonometric formula, and tan inverse x plus tan inverse y is v, and x plus y by 1 minus xy is u. This is u. So this is the relation between u and v. Okay, this is the relation between u and v. Very simple. See, in examination, the small changes may occur. Instead of this plus minus plus, sign may get changed. Means you may be given x minus y by 1 plus xy tan inverse x minus tan inverse y. In that case, here minus, here plus, here minus, here minus, here plus, here minus, then again the same thing will be. Okay, so this type of small changes may occur in examination. Now, quickly we are going to solve third one. Now, these two variables problem we discuss. Again, one more problem on two variables. Solve. The question is like this: check the functional dependence of these two functions, and v is x plus y by x. We are going to check the functional dependence of this. Okay, and if they are functionally dependent, if yes, find relation between them. Find relation between them. Let's try to understand the question. If they are functionally dependent, then you go for relation. If they are functionally independent, means Jacobian is not zero, so no need to find out relation, because we cannot find out relation if the functions are functionally independent. Okay, the functional dependence, this dependence is must for finding relation. Now the same procedure again. So what is the difference between the previous sum and this one? In previous sums, one of the variable means u or v, the trigonometric function was there, or inverse trigonometric, whatever. But here in both the cases, in u and v, we have algebraic functions only. Okay, this algebraic function, this algebraic function. But first thing is to find out, is to check the functional dependence. Here, J is the Jacobian. Jacobian I am writing for two variables in this way. And this is del u by del x, del u by del y, del v by del x, and del v by del y. By definition of Jacobian. By definition of Jacobian, I have written. These four derivatives are required. The four derivatives, try to find out separately. Four derivatives I am going to find separately now. See, the first derivative is required. U is x minus y by x plus y. Very quickly, del u by del x I am finding. Derivative with respect to x, keeping y constant, but x is present in numerator as well as in the denominator. The quotient rule I am going to use. Denominator square, denominator here, derivative of numerator with respect to x is 1 minus numerator, and derivative of denominator with respect to x is again 1, and this is coming to be, writing directly, x plus y square, and if you simplify it, the x and x will get cancelled, y plus y is 2y will remain in the numerator. Okay, now del u by del y I am going to find. Take derivative of u with respect to y, keeping x constant, but y is present in numerator as well as in denominator. Therefore, use quotient rule of the derivative. Denominator square, here denominator, derivative of numerator with respect to y minus numerator, and derivative of denominator with respect to y is 1. Okay, I am not explaining much because the sufficient practice on partial derivative is done now. So partial derivative of complicated function you have found. Now x plus y square. Here after simplification, writing directly after simplification, is minus x minus y minus x plus y. Plus y and minus gets cancelled, minus 2x will remain. Okay. Now I am going to find del b by del x and del b by del y. So for the sake of simplicity, you can directly take derivative, but for the sake of simplicity, in the denominator single term is there, in the numerator two terms are there, x by x is 1 and y by x like this. For the sake of simplicity I have written. You are free to take derivative directly also. Now del b by del x, derivative with respect to x, derivative of 1 is 0, derivative y is multiplicative constant, and derivative of 1 by x is minus 1 by x square. Is it? Now del b by del y, derivative with respect to y, derivative of 1 is 0 and derivative of y is 1 and 1 by x is multiplicative constant. Just quickly we found the derivative for these four derivatives. Putting values of all those four derivatives here. What is del u by del x? It is 2y by x plus y square. What is del u by del y? It is minus 2x by x plus y square. Is it? Del b by del x is minus y by x square and del b by del y is 1 by x. Now have the product of these two. We are going to solve determinant, 2 by 2 determinant. If you multiply these two, so 2y by x plus y whole square minus product of these two is plus 2x. Here I am writing directly. If you multiply these two, minus minus will be plus, 2 I am writing, and 1x will get cancelled, only one single x will remain in the denominator, y will be there in the numerator, and x plus y square will be there in the numerator. Directly writing. Now these two are same with opposite sign, so it is 0. This implies that u and v are functionally dependent. Okay, but what is the question? Check they are functionally dependent or not. So we have checked is u and v are functionally dependent or not, and Jacobian is coming to be 0. Therefore, we can state u and v are functionally dependent. If they are dependent, then we are free to find out relation. So we are going to find out relation between u and v. We are going to find out relation between u and v. See, u is given to you x minus y by x plus y. V is given to you, directly writing in this way, 1 plus y by x, 1 plus y by x. Because when you take separate denominator, x by x is 1 and y by x, like that. Now if you look at these two variables very carefully, u and v, so what is our target? Our target is to remove x and y. Once you remove x and y, so you will get relation between u and v. The removal of x and y is our job to find out relation. So if you look at this very carefully, so we can find y by x. This one I have shifted here. I found value of y by x. I found value of y by x. Y by x is v minus 1. And here, if you look at this carefully, this algebraic function, so I am dividing this numerator by x and denominator by x in this way. This u also I have written in terms of y by x. Now you are free to put value of y by x. Y by x is v minus 1 and y by x is v minus 1. This 1 plus 1 is 2 and this 1 gets cancelled, is v. Therefore, this is the relation between u and v. This is relation between u and v. But this relation you can find out yours also. Have cross multiplication, find value of x, put it here, then y will get cancelled, y will automatically get removed. Or find value of x from here, and put the value of x here. Okay, then removal of y will get. In this way, that way you can do. That way you can solve this problem. Okay, now we discuss about the functional dependence and independence. I repeat, when the functions are functionally dependent, if its Jacobian is 0, if Jacobian is 0, then they are called functionally dependent. And if the functions are functionally dependent, then we can find out relation between them, otherwise not. Now very quickly, we are going to solve the same problem, but I am going to take 3 variables. Here we check the functional dependence for 2 variables only. Now we are going to find functional dependence between 3 variables, amongst 3 variables. To check the following functions are functionally dependent. Or not. If they are functionally dependent, find relation amongst them. Is it? The functions are u is equal to x plus y plus z, this is the first function. Okay. V is equal to x square plus y square plus z square, and w is equal to xy plus yz plus zx. We have only 3 variables now. Previously we did with 2 variable problem. Now this is 3 variable. So we are going to check the functional dependence. It is very clear to find out the value of Jacobian. Jacobian for 3 variables like this. For 3 variables. Now by definition of Jacobian, it is del u by del x, del u by del y, del u by del z. Okay, first row for u, second row for v, and third row for w. Okay. Now all these 9 derivatives we want to find derivatives very carefully. The derivatives I am going to find out separately here. These 9 derivatives I am going to find out separately. See, what is u? X plus y plus z. This is u. Del u by del x with respect to x means derivative of u with respect to x, keeping y and z constant. Derivative of x is 1, derivative of y is 0, derivative of z is 0. Del u by del y, derivative with respect to y, keeping x and z constant, it will be 1. Del u by del z, again it is coming to be 1. Okay. Now for v is what? X square plus y square plus z square. Derivative of v with respect to x is 2x. Derivative of these 2 terms will be 0. Derivative of v with respect to y is 2y. Derivative of v with respect to z is 2z. Is it? Now derivative of w with respect to x, w is xy plus yz plus zx. Del w by del x is derivative of w with respect to x keeping yz constant. Derivative of x is 1, y is multiplicative constant. Derivative of this is 0. Derivative of x is 1 and z is multiplicative constant. Del w by del y with respect to y now, keeping x z constant. Derivative of y is 1, x is constant. Derivative of y is 1, z is constant. And derivative of this term will be 0 because z and x are constant. Del w by del z now. Z is variable, x and y constant. Derivative of this is 0. Derivative of z is 1, y is multiplicative constant. Derivative of z is 1, x is multiplicative. In this way. Is all these 9 required derivatives we found. Now, putting values of derivatives here. Del u by del x, del u by del y, del u by del z, all are 1, 1, 1. Del u by del x, del u by del y, del u by del z, 2x, 2y, 2z. Derivative of w with respect to x, y, z, here y plus z, del w by del y, x plus z, and del w by del z is y plus x. Okay. Now, try to solve this determinant. If you solve this determinant, while solving determinant, you can use properties of determinant also. If you are free to take 2 common from second row in that way. Or without using property of determinant, you can solve it. No problem. Now, if you solve this determinant, the value is coming to be 0. Okay, you will not waste time on solving determinant because you are very expert in determinant now. The value of this determinant is 0. This implies u, v, w are functionally dependent. The first part is over. Okay. Now the second part. Whenever 3 variables, because we found relation amongst between 2 variables. So when there are 3 variables or more than 3 variables, you have to be very careful while finding relation. Okay. Because the relation, how do you get? For relation, we want removal of xyz. And once you remove xyz, by solving these 3 equations, in the next step you will be getting relation. Okay. Now look at these 3 functions very, very carefully. If you look at these 3 functions very carefully, here the degree of each and every term is 2. Degree of each and every term is 2 here. Okay, when we have the product of 2 variables, we have to add degree. Degree is 2, 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 degree is 2. Okay. But here we have degree 1. So to get these values repeated, it is very clear to have the square of this. See, there is no logarithm or method to find out relation. It's logically you have to think and you have to see how the x, y, z will get removed. Okay. Here I am going to take square of u. I am going to take square of u because if you take square, the degree of each and every term will be same 2. Now, square of this what? A plus b plus c whole square is what? A square plus b square plus c square plus 2 times x into y, then 2 times x into z, okay, 2 times x into y and 2 times x into z plus, now the term of x has been exhausted. 2 times y into z, y into z. The term of y is also exhausted. Okay, in this way you can remember the expansion of a plus b plus c whole square. Here we have square term of u, and the degree of each and every term in u square is 2. 2, 2, 2, degree 2, degree 2, degree 2. Okay, degree of constant is being considered as 0. Now, is there any possibility that to have the combination of u square, v and w? Okay. But if you look at this equation very carefully, x square plus y square plus z square can be written as v. Okay, if I write like this is v, and 2 times xy plus xz plus yz. Okay, then v u square plus 2 xy plus xz plus yz, xy plus xz plus yz is w. This is the relation amongst u v w. Relation amongst u v w. In the relation of these 3 variables, x, y, z, this right hand side variable should be absent. We don't want relation x, y, z on the right hand side. Okay. So this is relation amongst u, v, w. So this was, we discussed about the functional dependence. This is very important application of partial differentiation. In next lecture, we will be discussing one more application of partial differentiation. Thank you very much.